Um, okay. Good afternoon, everyone, and welcome once again to the Economics webinars. We are honored to have with us engineer Juan Jiménez. He's working at Kestrel Resources, and today's presentation is titled Mine Ventilation in Longwall Coal Mines. Without further ado, it is my pleasure to hand it over to Engineer Jiménez.
Good
Good
afternoon,
afternoon,
everyone.
everyone.
Thanks for coming to this presentation. I will start sharing my screen. Can you see it?
Yes, we can see it.
Yeah, cool.
Yeah, cool.
So, good
Good
afternoon.
afternoon.
My name is Juan
Jiménez,
Jiménez, and today I'll be presenting mine ventilation in Longwall coal mines. So the reason of this topic is I remember my old days in uni, and we used to talk about more about hard rock mining. So I wanted to give a different insight of mining, and this is what I've been working on for the past 3 years, which is coal mines. Agenda. Today I will be talking about myself, then coal formation, composition, properties, and uses. About Kestrel, the company I work for. Hazards in coal mining. Then ventilation control devices. Gas monitoring. Ventilation in a development panel. Ventilation in a Longwall panel. Management of active gove. Management of field gove. And software. So here we have some new terms for you. For example, gove and ventilation control devices. It's maybe new for you, but I will be explaining that later. So about myself, background, I studied at the Pontifical Catholic University of Peru. I finished my bachelor's there. And then I went to Curtin University in Western Australia and finished my master's degree in mining engineering. Right after that, I started a vacation placement at Kestrel Resources for 3 months. And then I was promoted to a graduate mining engineer, which I'm currently doing. In terms of software, I use Microsoft Office, that's very basic for everyone. Then Benzim, which is a ventilation simulation software. You may know about it. Safe gas, easy gas, and C gas. I'll be explaining a bit that later. AutoCAD, Aviva, production management. So this is Aviva is a database that helps you with your production and delays and all that sort of stuff for production. And then Pi Data Link and Pi Vision. So Pi is another database that we use. We can store their tags, for example, temperatures, pressures, and real-time data. And then Pi Data Link is a tool in Excel, so you can retrieve that data, and then you can later use it for your own reports, do your own calculations in Excel. And PyVision is a tool that allows you to create dashboards. So you can set up a dashboard and see in a trend the data that you want, and you can also set up automated emails and a bunch of calculations. So it is very interactive and very useful. About my role at Kestrel, so I work for two departments. One is mine planning and the other is ventilation. So what I do in my planning is production reports and data reconciliation. So the production reports, we do them weekly and monthly. And then we reconcile the data, applying calculations made by the surveyors. And we use Aviva, as I mentioned. And yeah, Aviva helps you also for the reconciliation part. Then we have permit to mine. So the permit to mine is a document that allows you to mine a certain area in the mine. So before even attempting to mine an area, you have to assess the risks and the controls that you have in it, in the most important aspects, which are ventilation, geotechnical, gas drainage, compliance, emergency escape ways, and all those sorts of stuff. And then when it's signed, fully signed, then we can actually mine it. Then we have mine plan change. So that's another document that requires assessing the same areas as mentioned: ventilation, geotechnical, and the rest. And yeah, as you may know, mining is a very dynamic environment, so having those documents to assess the risks and the changes is very important. Then we have the forecast. Forecast is a set of documents that we do every month. Um, so that layouts the sequence of mining for the next months and also years. So it gives an indication to all the departments on what is the intention, where are we going to mine, when are we changing to different location, and the most important events. So I also help with this one. Um, then for the ventilation part, I help with the ventilation surveys. So a ventilation survey um, is a full day underground in which you gotta take data from several ventilation stations in terms of air velocity, gas concentrations, temperatures, everything that is related to ventilation. And then you have the ventilation reports. This is a statutory requirement per legislation. So we use this data from the ventilation survey, and then we perform calculations. And we also talk about other aspects of ventilation, such as dust, thermal stress, leakage, and the general performance of the mine in terms of ventilation. Other aspect that I also help with is the permits. So in underground mining, we have what is called real-time gas monitoring, a bunch of sensors underground that record in real time, and some of them have triggering functions, which allows you to turn off the power of certain areas for safety. I will explain a bit more about this later. We also have the tube bundle, which is another monitoring system. Yeah, I will explain this one as well. And then the ventilation control devices. Then for tube bundle calibration, for the tube bundle, I also help with the calibration of it. Then we have benzene modeling. Suspension is a ventilation simulation software. I help with that one. And then the development and maintenance of BioVision dashboards. So now I wanted to give an introduction also of coal, formation, composition, properties, and use. I'm sorry, there's wait a second. So there's in the screen floating the camera and all that. I'm trying to hide it. Yeah.
We actually don't see that person. Don't worry about it. It's.
Oh yeah, but I can see it, and it's.
Okay, no problem.
Yeah, but it's all good now. So yeah, I'm not an expert on the formation of coal and stuff, but I still gather some information. So most coals were formed between 60 and 300 million years ago in a process called coalification. It all starts with plants in a swampy environment, as you can see here. And that is important because the water is protecting the plants from oxygen. And then these plants die and then they accumulate at the bottom. And After some time, it forms a very soft material called peat. Then, as time passes, then sediments form, and then this peat is further buried. And with enough time, heat, and pressure, then it becomes the lignite. And you see time and pressure. And then the coal can be, there are four types of coals, or also called the four ranks of coal, which are the lignite, the subbituminous, the bituminous coal, and the anthracite. So all these are done in sequence, and the more heat and pressure the initial peat is exposed, the further it progresses to the next stages. For this presentation, I'll be focusing on bituminous coal, which is the most common coal in underground coal mining, and the one that also Kestrel produces. Yeah, composition for bituminous coal is mainly carbon, and then some minor percentage of hydrogen, nitrogen, sulfur, oxygen, ash, and moisture. About the properties, well, you may know this one. It is dark brown to black. Hardness, it is actually soft. You can even break it with your hand. Density, it is has lower density than many rocks and minerals. So at Kestrel, the coal density is about between 1.3 and 1.5 tons per cubic meter. Porosity, it can be very porous, and it allocates methane and other gases in its pores. So this one is very important, methane. It is a serious hazard in coal mining, and there's a section for that in this presentation. Then you have the luster. It is dual to shiny luster. And then the uses. So bituminous coal is also divided into two types. One is called the metallurgical coal, and the other the thermal coal. So the metallurgical coal is used for steel making, and it has the following characteristics, which is high carbon content, low ash content, and the coking ability. So the coking ability is the ability for the coal to, when it's heated, it becomes into a plastic-like mass, and then it hardens into a much harder material in order to make steel. And then we have the thermal coal, and it is required to, well, that is used for as an energy source, and therefore it needs to have a higher calorific value and a higher volatile content. Now, I would like to talk about Kestrel. Most of the data here is taken from Kestrel. Give me a second. I think it is a good example. I just wanted to make that a special mention. Kestrel mine is located 4 kilometers north of Emerald in the Queensland Bowen Basin, and it's been in operation since 1992. Underground coal mine, production of about 7 million tons of coal per year. Its depth is between 350 and 400 meters. The same thickness between 2.5 and 3 meters, and the mining method is the Longwall. So we have here a picture of one of the Longwalls, far one, the one that is currently being mined. So by looking at this, I can mention some of the concepts, important concepts in longwall mining. So in longwall mining, all the resources are divided into longwalls, which are like rectangles, as you can see here. And then the method consists in creating these two headings, typically two headings, to access the last part of the longwall. So you do this by using a machine called a continuous miner, You can mine all this. That is called the development. And then you need also to mine this one to be the other end of the Longwall phase. So this will be the initial Longwall phase. And then there's a type of machinery, or I would say equipment, called the shields, which hold the roof. So when you start mining, nothing falls on the workers on the other machinery. So you have your shields holding your roof, and then you need the cutting machine, which is called the sheeter. So the sheeter, what it does is, it starts here, it mines, let's say, a meter of coal all the way to the other end, and then it comes back and keeps going like that, retreating. And the shields advance with the whole machine, the whole equipment, and it keeps retreating. And at the very end, you get here. We can see some dashed area. That is the gove. So the gove is the remaining part of the mining, which is made of stone, some remnants of coal as well, and it's full of gases like methane. So the gove is a very dangerous place. You can see the dangerous sign here. So what we do is try to isolate that. In these sections, we have something called the seals. The seals, which are like a wall of concrete. So that way we isolate the gove. And you can see, for example, here there's another Longwall. That was Longwall 500, but it's now fully completed and fully sealed. Yeah, so those are some of the concepts. Yeah, we have here the dimensions as well. So these long walls can be very wide and long. This width is 400 meters approx, and the length is about 5 kilometers. It's a very efficient method. Here I have a video for you that shows a long wall phase and the machinery, so you have a better idea of what I'm talking about. So that machine that is cutting is the shearer. And you can see at the roof, there's those are the shields holding the roof. And the coal mine worker is there, safely protected by the shields. You can see at the bottom the coal is being moved. So at the face we also have a conveyor to transport all the coal, and then it goes back to surface. You can see the shields are moving. So that way we keep retreating the whole system as we mine. You can also see the water sprays there. So as the machine is cutting, it of course gets hot. The sprays help to cool that area. Yep. That was the video. I'll continue with hazards. So, as mentioned earlier, one of the biggest hazards is methane. It is a gas, and it is also present with the coal. So, whenever you have coal, you most likely have methane. The formula is CH4. It has the following explosive ranges, which are between 5 and 15% methane, and you also need oxygen as a minimum of 12%, which is what we call the nose point. So we have this graph, which is called the Coward's triangle. It shows that in the x-axis we have methane, and the y-axis we have oxygen. So methane is explosive zone, which is this small triangle. It ranges from 5 to 15%, and the oxygen here that is 12. So you can have also different zones in this graph, which is one is called the uh, fuel-rich zone, which is a lot of methane and not enough oxygen. And you can have the opposite, which is the fuel-lean zone, which is a lot of oxygen but not enough methane. And then you have the safest zone, which is this one, non-explosive zone, which is not enough methane and not enough oxygen. Then, yeah, it is a steam gas, as mentioned. There's another steam gas, very common, which is CO2, but it's not as dangerous as methane. And I have an excerpt of the regulations. By the way, this is the regulations that coal mines follow in Queensland. And this is the section 3431C. So the ventilation officer for an underground mine must ensure that the mine's ventilation system is designed, implemented, and monitored to ensure the atmosphere in each part of the mine has a general body concentration that is for methane no more than 2.5%. So there's a bit of leniency between this 5 and the 2.5. Another term for this is ventilation officer. So that's the person accountable for and responsible of the ventilation in the ventilation system in the whole mine. The next point, the regulations also states the location of methane sensors as a minimum under tripping requirements. So by tripping requirements, I mean the function that they have in order to turn off electricity. So as mentioned, methane is explosive. So equipment in some areas that have electrical tools and equipment, they have sensors that whenever they reach a certain level of methane, immediately they turn off. Well, first they alarm and then they turn off. This is a safety measure, and I'm not going to mention all of them because it is very extensive, but you can check it in the coal mine safety and health regulations. I also provide a reference at the end of the presentation. Sorry. The next hazard is spontaneous combustion. So coal is by itself an energy source, so it has the ability to self-heat whenever it's exposed to oxygen. This process called combustion. It is an exothermic reaction releasing heat, and then spontaneous combustion occurs when this rate of heating of coal is higher than the rate of cooling. That means that in the worst conditions, a piece of coal or an amount of coal can self-heat until the point it becomes, its temperature goes up to very high values, and then an explosion happens. So this is a bit of the evolution of spontaneous combustion. These are only referential values because coal is different from mine to mine, but it gives you an idea of what usually happens. Give me a second. 10 to 30 degrees, that's the ambient temperature. From 30 to 50, we start seeing CO and CO2 form. From 50 to 100 degrees, we have hydrogen forming, methane, another gas called ethane that is formed as well. And then at 150, ethylene appears. So this gas is very important because it's an indication that we're achieving this temperature and that something really bad is about to happen. And that is also the typical thermal runaway. So thermal runaway means that from this point, from this point, the temperature increases exponentially. So let's say from the ambient to get here, it can take weeks or even months. But from 150 to the latest 600, it could happen in even hours. So this is a very dangerous place to be. Then from 150 to 350 degrees, we start seeing physical indicators like gray smoke, petrol-like smell, haze, and others. And then at 600 degrees, that's the minimum ignition temperature of methane, which means because the coal is too hot, it can actually trigger methane and create an explosion. So some of the indicators that we use to assess how is the spontaneous combustion going is the Graham's ratio, which is the CO generation and oxygen deficiency ratio. So as the combustion progresses, oxygen decreases and CO increases. So therefore your Graham's ratio increases, and then that gives you an indication of what's happening. Your CO concentration as well, that gives you an indication that spontaneous combustion is still in an early stage. And then you have your ethylene concentration, which, as mentioned, shows that something very bad is happening. This is usually the trigger to make everyone out of the mine because it's very dangerous. Oh, excuse me. I've been talking for too long. The next one, dust. So dust is also important. It is often a bit ignored because it's not as dangerous as explosions and spontaneous combustion, but it's also important. It is generated from mining and transport of coal and vehicle movement, and it's floating around. So we have different types based on the size and the components. Spirable dust are the larger particles that affect the nose, the throat, and the upper lungs. So this one is annoying, but cannot cause like very bad illnesses. Unlike these two materials, which are the respirable dust and the respirable crystalline silica. Both are particles less than 10 microns that can actually reach deep into the lungs. And the first one, respirable dust, is referred to just coal dust, but the other one is referred to silica. So the regulations also have their limits. So you cannot have for respirable dust more than 1.5 milligrams of cubic meter in an 8-hour shift. And for respirable crystalline silica, the limit is 0.05 in an 8-hour shift. If your shift is longer, there are methods to convert to convert into that. You gotta specify which method you are applying. And then the consequences for respirable dust, it is bronchitis or irritation, which is not so bad, but this one's very bad, and you may also know it from your hard rock mining. Pneumoconiosis or black lung, and silicosis from the silica. So yeah, those were the hazards. Now I want to talk about the ventilation control devices, which are very important. So their purpose is to direct the air through the mine as required. And they must, the rating of these ventilation control devices must meet the requirements of the regulations. There's a section called the Schedule 4, which states the requirements in terms of, for example, if we grab this one, the stopping overcast of regulator installed in the main ventilation system, it's got to be capable of withstanding an overpressure of 35 kPa. And we have a bunch of seals here withstanding the same 140 kPa and so on. So what does that mean? The ventilation system in the mine is is mainly driven by the main fans on surface, which create a very high pressure so the air can flow. Then there are some areas in which you have an intake air and then a return, which creates a differential pressure between both in your ventilation control device. So this pressure can be as low as a couple of hundred pascals, but if it's about, it can also get up to 3,000 pascals, and that is very hard. If you want to open a door between a BCD that is like that, it is very hard. So it's gotta be robust and withstand that pressure, and that's why of the high requirements for this pressure. Assume that it fails, then you can have many things. It can be, you can have recirculation, you can have dead spots, and yeah, it's something that you don't really want. So that's why of these requirements. Then I'm gonna show some of them. We have stoppings, which is a wall that separates flow between two airways. Can include a man or not. There is a very basic BCD. Then you have machine doors. There are BCDs that allow for vehicle access. So it is not as a stopping. It also separates flow, but it can also open from the middle to allow vehicles to travel. Then we have a coffin seal, which is a stopping with a hole with flaps that prevents short circuiting in a panel belt. Well, this should be a roadway belt, sorry, while still allowing coal to exit the panel. So you can see a picture of that in here. You see, like it is like a wall with a main door, but you also have a hole in which the conveyor belt is passing, and you can get the coal out of the panel. So there are designated roadways in which you have this conveyor belt running all the way. And of course you need an exit to that, and also prevent airflow going as much as possible. That's why the importance of the coffin seal. Then we have an airlock. Is the term used to refer to a device that allows for a main or vehicle transport without affecting the ventilation circuit. It can be two sets of machine doors, two stoppings with main doors, or a coffin seal airlock box. So we have here an airlock box. The idea is that there's always either this door at the back or this door at the front closed, so air doesn't travel and you often use these ones in high pressure areas. So you open this one, you enter, then you close this one, and then you open this one, and you exit, and you close it again. So that way you have an airlock. Then we have overcast and underpasses. That is a BCD that allows to create crossover between airways. This is a picture of an overcast. So this at the bottom, you have the airflow going into the screen, and then at the top you have airflow going at the top. So that way you have air crossing. Another important BCD is the regulator. That is BCD that, as its name says, regulates the flow passing through it by increasing or decreasing its own resistance. We have a picture of that in here. This type, there are different types, and this one has louvers. That's the one that we use at Kestrel. And you can regulate the louvers to like totally close them, and also have them totally open or in between. So that way you can regulate how much air is going into that panel, depending on the requirements. And then you have seals, as mentioned earlier, that is a high resistant BCD made of concrete that isolates the gulf. So this one is thicker than a regular stopping. It has to be very thick so the gulf doesn't leak out too much. Because the gulf is an accumulation of rocks, coal, and gases. It can have a lot of pressure, and it will try to escape, to breathe out, and that's why we use the seals. Then we have Bratties and Butcher's flaps. These are temporarily BCDs. So for Bratties you can use it as a stopping, but it's not very hard. It's only used for temporary purposes. Bratties, by the way, is like a plastic material. So yeah. And then you have the booster flaps, similar to this, but they hang from the roof, and they can actually allow vehicle access, vehicle passing by. And yeah, they are not rated. Now we have gas monitoring. At Kestrel we mainly have three. The first one is the real-time gas monitoring. As mentioned, there are sensors placed strategically and to comply with regulations. So just like a box on the rib, and then it measures your gases. Typically is CH4, your methane, your carbon dioxide, your carbon monoxide, and your oxygen. And so the pros, they provide immediate readings, that's why the name, and they can include tripping functions. As mentioned, if you gotta protect an area, you can have your an area with electrical equipment. You can have your sensor there. It reaches some level of methane and it trips power. And then cons, it is difficult to calibrate because you can have, let's say, 30 of these underground, and then you gotta go to each one and calibrate each of them. So it is a very hard task. And then second, they are subject to an underground environment. Yeah, of course, they are subject to moisture, dust, getting damaged by vehicle or equipment. Yeah. And then the next system is the tube bundle. So it consists of the tube bundle hat, which has the gas analyzers on the surface, and then you have a set of tubes that go underground. So it is like having a laboratory on surface, and then from there are tubes that go via a borehole or from the main access as well. They go underground. And then what they do is you put them in a specific locations, and they grab the gas. So there's a pump at the surface. The gas sample goes all the way from underground back to the surface into these analyzers, and then you can get your sample and your gas concentrations. It utilizes safe gas and C-gas software. So safe gas is the software to manage the computer and the analyzers and the system, and C-gas is just to show the data in trends and plots and to show the data easily. So the pros, it is less likely to be affected by underground environment. Of course, the analyzers are on surface, so the only thing that can be damaged are the tubes. And yeah, the tubes are not as expensive as a sensor, so it is good economically. And the second, it allows for seal monitoring. So as mentioned, the seal is holding the gauge, and you cannot have a sensor there on the other side because no one can access that. The seal is sealed and no one can access. But you can have a tube running through the seal, and then that way you get a sample and you can know what's going on there. That's how you know if you're having a spontaneous combustion or it is totally inertized. So it is a good system. And then we have the calibration is relatively simple because you gotta calibrate only your analyzers on surface instead of having to calibrate 30 sensors. You only calibrate a couple of analyzers. And number 4, allow for obtaining a gas bag sample. So you can actually get a sample of the actual environment underground, which is very useful for for this one. I'll explain soon. We have the cons. The draw time can be extensive, plus 2 hours. So because the tubes go from underground to surface, it's gotta run all the way, and it can easily be 2 hours. So it is not actually real time. So that's a very important con. Yeah, the next one. Relatively difficult to install. So you gotta run the tube all the way from the top at the bottom. So yeah, that's another difficult task. The number 3, limited in number of tubes. So yeah, the tube on the hat. Well, it depends. Ours can analyze up to 30 points, 30 tubes. But in case you need more, then that's it. That's the maximum. Unless you get a new tube on the hat. Then we have the gas chromatograph. So the gas chromatograph is it's also on surface. It is like a box that it is like an analyzer inside with a computer, and what you gotta do is put your gas bag. You can either obtain it by the tip handle system or actually going underground and getting it. So you insert that, the gas goes into the analyzer, and it uses this method. So it's a very thin column that in which the molecules in the sample are broken down. So it separates the molecules, and then based on the thermal conductivity, the gas concentrations are measured. And it utilizes EC-gas and C-gas software. So similar to the tip handle and safe gas, EC-gas is the software that allows you to manage this system, the computer and the analyzer itself. And the C-gas is the same, just to represent the data in plots and prettier. And then you have the cons. It can detect gases at the real time that tip handle cannot detect, like ethane, ethylene. This is very important. Ethylene, indicator of spontaneous combustion. So the real time has the typical four gases: CO2, CO, CH4, and oxygen. Chupando has the same, but the gas chromatograph gives you more details. So in terms of precision, it's the best. It's understood to be more accurate than other methods. Yep. But you have the cons. It depends on gas bags. Then the second is that the calibration is daily. In this section, I'll talk about ventilation in a development panel. So typically 2 heading panels, 1 intake and 1 return, regulated at the dogleg. So the dogleg is like the very bottom of your return. It's the last section in which you can have a regulator there. Regulate how much air is going. So in this one, this is Menkefov 2 LF panel from Kestrel. The blue line is your intake, and then you can see here an opening. That is what we call a cut through, the last open cut through. That's why the CT. So it goes into 31 cut through, and then it returns into the return. So that's your circuit. Then stops are ventilated via auxiliary fans with ventilation ducts. So when the miner creates this opening, it continuously mines. That is called a stop because it is like a dead end. And you have your circuit from intake to return going into 31 and then going back, but you have nothing here. So in order to create a circuit, you have your duct going into this stop. So air can go from 31 into the stop, and then it goes back through the duct into the auxiliary fan. And the same applies for this fan ventilating this other stop on B heading. Typically the one on the left is A heading and the one on the right is B heading. That's how we name it at Kestrel. And then the ventilation in the use of auxiliary fans needs also to meet the regulation. And it says the ventilation officer must ensure that an auxiliary fan used at the mine is located and operated in a way that prevents air recirculating through the fan. And in order to achieve that, we use this next point. The BO must ensure that the minimum quantity of air flowing in any panel at the mine is the sum of the open circuit capacity of each fan. So each fan tells you in the nameplate how much it is supposed to be flowing. And then 30% of the open circuit capacity of the largest auxiliary fan in operation in the panel. So yeah, you have here the calculation, you do your math, and then you get a quantity of 40 cubic meter per second practical. And that's usually correct, but that's the minimum. Ultimately, the quantity necessary to comply with regulations, that's what you gotta use to safely dilute contaminants and provide adequate air temperature. So in here, I want to show the whole mega file 2. So you can see here in the heading, well, this image is cropped, but you have A, B, C, and D. This is your main system, and then you have your development panels. Another thing that I forgot to mention is that for Longwall, you remember when I explained about the Longwall phase, and you have one development on one side and on the other side. So the one that is the intake of the Longwall is called the main gate, and the return side is called the tailgate. So that's another term. And so what I want to show here is you have all the items that I mentioned. You have in here an air crossing or overcast. Then the air is going in this blue line as an intake and goes all the way up to the bottom of the panel. And then you have the red going back. And then this this area is what we call the dogleg. And this R is a regulator, which is controlling how much air is going into this panel. Then we have these green boxes are the real-time gas monitorings, with some of them with tripping functions. We have another one here. And these all are methane, methane, methane. This is CO. All of those requirements are in the legislation. And then you have this one, as well as per legislation, you have your basic four gases, CH4, CO2, CO, and oxygen. And we also have a tube bundle point. Tube bundle 28. Yep, that's in here. These are the stoppings, airlock stoppings, because at the beginning of the panel, it is expected to have higher pressures. That's why you gotta have an airlock. Yep, that's the next. This is mid panel. So we start, of course, at one cut through, and then we can see here 23, 24. So these panels can be very long. This one, I think it is like 5 or 6K, 6 kilometers. Yeah, so they can be very long. And because of that, they pick up a lot of heat from the ribs, and from machinery as well, from everything that you can have. And that's why at Kestrel what we do is we have at mid panel 2 intake boreholes with cool air. So at the surface we have chillers and a hot refrigeration plant to send chill air to control those temperatures. It is also the responsibility of the PO of the ventilation officer to control the air temperature. That was development. Now, ventilation in Longwall panel. Longwall is often the open circuit of the mine, so it often doesn't have a regulator, because you gotta send more air to that. Typically 50 to 70 cubic meters per second at the Longwall phase. There's a split in the main gate to maintain the belt rod ventilated, which is regulated at the dogleg regulator. I'll show you an image later, just explaining this. The typical homotropal belt to send heat and contaminants away from the Longwall phase. I'll explain as well with the image. And we have extensive real-time gas monitorings to protect the transformers, equipment in Longwall and others. So this is current Longwall for Juan, start of panel and the Longwall phase. So this A heading is the belt road. So as you saw in the video, the shearer is cutting in here. There's a belt moving to this direction, and then the coal gets in here and it goes all the way to A heading, back to the mains, and then back to surface. So we have here an air ventilation split, 25 cut through. So the intake goes from this back to here, and some of the air goes into the Longwall phase, and the other returns into A heading. So when the coal is going in the same direction as the air, that's what we call the homotropal belt. And that is good because it's sending the heat and everything away from the Longwall phase. Because the Longwall phase can be a very hot place, and you want to maximize that. What else did I mention in that? Mention split, this, yeah. We have also extensive real-time gas monitoring sensors. You can see here 3, there's another one in here. So yeah, the Longwall is the area that has the most Another concept, this is the Gulf, forms as we retreat. You can see much better here. These boxes, these are the seals isolating the Gulf. We also have them in here. And yeah, that's your Longwall. Oh yeah, let me go back for a second. So the Gulf that is being formed in your Longwall phase, the current one, that is called the active Gulf. And the one that you already mined in the past and is fully sealed, like this one, that is called your seal Gulf. So as I mentioned, the Gulf can have contaminants, gases, and stuff. All of that is pressurized, and it will try to escape through the seals, or well, through these areas, and that's why you have the seal. That's one way to manage that, but there are other ways as well to manage the Gulf emissions, which is very important. Management of active Gulf. So first you have your ventilation control devices, in this case seals, to restrict the air entering the Gulf. So it is not only dangerous that Gulf breathes out, exits the seals, but it's also dangerous when it goes in, because you remember the spontaneous combustion. So if you have air going in, that means oxygen is washing the coal, which creates the combustion process. And if it's not treated correctly, it can lead to spontaneous combustion and then a massive disaster. And I have a picture of that in here, how this happens. So the seals are not perfect, either through this or through the Longwall phase itself. Air will tend to enter into the Gulf, and there's an area called the wash zone, in which air is washing the coal and mixing with the methane and all of that, and then it exits the phase in something called the Gulf Stream. If you are in this point, you can also actually feel the Gulf Stream. If you raise your hand there, you can feel it warm, and that's all the gases exiting through that area. To manage that, you can also have the active Gulf drainage, which is a bunch of boreholes and a bunch of pumps on surface to drain the Gulf, and also try to hold the Gulf Stream a bit. If you drain the methane, then there will be less going into your Longwall phase. But you cannot also, you cannot either push too hard, because if you try to drain the gas very hard, you can also make a lot of air going in. So there has to be a balance. It's not like too much of this or too much of that. It's gotta be balanced. And that's what I put here: active Gulf drainage and pressure balancing. Then the other one is the inertization using nitrogen injection. At Kestrel we use that as well. So we have nitrogen plants on surface, and then that goes underground via a borehole and pipes, and then that can go into your main gate and then connected into the seals. If I go back for a second, for example, you can have in beheading inertization line, and then another pipe connecting into the seal and inject nitrogen. So what nitrogen does, well, it also depends on the quality. Typically we have 3% or 2% oxygen, and that is a gas that inertizes, so it has less oxygen, is trying to keep the oxygen levels low. You remember the Coors triangle? We want to have less than 12% oxygen. Well, that would be the limit, but a good target is less than 5%. Then the gas monitoring, also real-time two-bundle monitoring, gives you an indication of how your Gulf is behaving. Back sampling from Gulf Stream or seals as well. that's another. But then you can get your bags, go into your gas chromatograph, and know how much, what the concentration of the gas is, and then take action. Then you have management of sealed growth. It's similar. You need your seals to restrict air going into your growth. Pressure balancing as well. You can also have sealed growth drainage. Then you can also inject nitrogen, that is very similar. And your gas monitoring as well, real time active bundle, and back sampling from seals. Then the last part is software. So I think benzene, most of you know, but just in case, we can help you with airflow simulation, heat simulation, and contaminant simulation. This is snip of the Kestrel mine model. You can see here at the top the three main fans. This is your main return. We have here B, C, and D, all in the mains. So yeah, that's what we use to model and to also create the permits. Whenever we want to make a change in the ventilation system, we use this to predict what is going to happen. Then you have safe gas. As mentioned, this is to manage the two-bundle system. This is nib of the screen. You have the mine. You can see here some numbers. These are the two-bundle points. So all is very logical. You have here on the sides the gas concentrations per point. And you can then also turn on, turn off points. You can select one to get the sample from it. So it allows you to manage all that system. Also in SafeGas you can do the maintenance of the two-bundle system. This is a snip of how it looks like. You can see all the 40 points. Well, actually, we have up to 30, and we don't use these ones. You can here see the pressure in the pumps. These cylinders, zero gas, all of this is for calibration. And yeah, here you have the readings of the two analyzers. You can switch between them. Let's say there's an error or something happening here. You can switch to the other one. So yeah, a bunch of data, very interactive.
Engineer, I'm so sorry, but your time is up. It's 2.05.
Okay, I'm just gonna pause the images then.
Okay.
This is the gas chromatograph. Yeah, sorry, I didn't see the time. It gives you your gas concentrations, the DCC gas to make the plots, and that was it. Then references. Any questions?
Okay. I think we don't have any more time for questions. We have another engineer waiting to open a Zoom. So
Okay.
thank you very much. This was.
I'm just gonna show the.
Okay.
Well, in case you have any questions, yeah, I'm sorry about the time.
Don't worry about it.
This is my email, and you can ask me anything you want there.
Okay, thank you very much, engineer. Once again, this was an enriching presentation, and for everyone at us here, and thanks to all of you who have joined us today. Y tenemos un último webinar que ahora voy a mandar el link por el grupo de WhatsApp. Thank you very much once again, engineer.
Thank you. Thank you very much.
Tu hijo está acá.